So we will start with shear stress. So far we were dealing with bending stresses. So in a beam, if it is subjected to some loading, you know that it will bend, and we are saying that it will be subjected to some bending moment as well as shear force at each and every section. So we know that when you take up any particular section, there will be bending moment at that particular section, and shear force also develop. So we have seen what is the stress developed due to the bending moment. That is bending stress sigma is equal to m by z, or m is equal to sigma into z. So we have derived the bending equation, which is equal to, you remember, I think m by I is equal to sigma by y is equal to E by R. From that, m is equal to sigma into y by I. So you will have the bending stress developed at each and every section. Similarly, due to the shear force also there will be shear stress. So if you take any particular section over here and you consider a delta x length, so in this you are just considering delta x length of the beam, so which I have shown here, delta x length of the beam. You can see that for this much particular length, if you take a particular cross section over here, you can see that the bending stress will be developed normal to that particular cross section, and you know that depending upon whether it is simply supported beam, there will be tensile stresses acting in the bottom fibers and compressive stress acting in the top fibers. So you have got the bending stresses acting like this. So this bending stress will be acting here as well as on this section. So if you have got some variation in between this end and this end only, there will be some shear force coming. I hope you understood, because you know that the relationship between bending moment and shear force is that variation of bending moment gives you the shear force, isn't it? So if ever you have got variation of bending moment only, there will be shear force. So between these two section lines, that means for this much dx length, you are saying that there is some variation of bending moment. So there will be shear stress acting. So that shear stress will be acting between the layers, that is shearing off. Understand? So if you take this particular end, you can see that the shear stress will be acting between the layers, so that to counteract this bending stress. Understand? So between these two sections, since there is an unbalanced bending stress coming, in order to counteract that unbalanced bending moment, so in turn bending stress, this shear stress will be developed in order to counteract that bending stress developed. So this is the shear stress which you are going to find out how you can analyze the shear stress developed in that particular cross section. That is what you are going to deal with now. So what I have told you now is that whenever there is a change in bending moment, only shear force will come into the picture. When only change in shear force, when bending moment comes, only shear force will come, as well as shear stress also will come. So if you take this as a cross section, this is B and D, there will be shear stress acting like this. So let us go to the derivation of that particular shear stress. So here you are considering that dx length over here. So I have told here two section lines I have taken, AC and BD I have taken here, and at this particular level you have got the bending moment as M, and at this particular level you have the bending moment as M plus DM. So that means there is a variation of bending moment between the sections AC and BD. So here the bending moment is M, here the bending moment is M plus DM, that is some variation is there. So if only variation is there, shear force will act. So these are the free body diagram which you are going to do like this. So now you are going to consider this particular level here and for this distance dx. So if you take a cross section over here, if you cut over here, this will be the cross section. So you are not saying that this is a rectangular cross section, this is of some cross section. So this is the cross section, but the width under consideration is B here. Understand? So if you take the section over here and draw the cross section, this is the cross section, and the width that cross section is B. This is the depth. So this is the neutral axis, and you are considering an element PQ of thickness dy at a distance y from neutral axis. Okay, so this is their level PQ over here, right? The thickness of the element is dy and it is taken at a distance y from the neutral axis. Okay, so as per the bending equation, you know that bending stress sigma is equal to m by z or m by I into y. So I have taken for this particular section, bending moment is capital M, moment of inertia of this cross section is I, and you are taking a level at y distance from the neutral axis. So at that particular layer, the bending stress is m by I into y. Okay, then you are going for total force on the face AC. So having got the stress, you can find out the force as stress into area. That is total force I have taken. So I have to take the summation. So I have taken m by I into y. That is the stress into area. What is area of cross section? That is B. This is the area under consideration. That is B into dy. So this hatched portion is the area, that is width is B and thickness is dy. So I have taken area as B into dy. This is the stress. Sorry. This is the area B into dy and this is the stress m by I into y. Similarly, we have taken total force in the face BD. So keeping everything constant, only thing is that in the face BD, the moment has changed from m to m plus dm, right? So m by I into y. So you have got m plus dm by I into y is the stress into area of cross section is B into dy. So you get the force in the level BD. So this is the level BD. So you got that particular force. So you have calculated the two forces. So you are going to take up what is the excess force between the faces AC and BD, because we don't know which is greater. So we have just taken the excess force as integral. Y to Y1 I have taken is that because we have taken this particular term difference, this particular term. So what happens? This m by I into y get cancelled. So the remaining value is dm by capital I into y into b into dy. Everything else is there. Only thing is that m gets cancelled out. So you will have dm by I into y into b into dy. So I have just switched over from sigma to integral. Why it is that? Because here we have taken an element over here at a distance y from the neutral axis. So this distance I have marked as y1, right? So this is the distance I have marked as y1. So I have to take the whole area above the neutral axis. So I have taken you have taken this level. So I am going to take up the area above this. So this is the 0 level and this is y level and this is y1 level. So I have taken the excess force between the faces AC and BD. I have taken as integral y to y1 dm by I into y into b. Understand? So into dy. So this dm is a constant because the bending moment is a constant value at that particular section. Capital I is also a constant. Then b into y into dy come outside, right? So this is the excess force coming between the faces AC and BD. Okay. So shall we write up till here?